Hi, this is Moser back with a tutorial on predicting the products of chemical reactions. So, by the time you are done with this video, you should be able to correctly predict the products that will form when you're given reactants. What you already need to know coming in, big one, is how to write correct formulas when you're given a compound name or when you're given two ions that may form a compound. You also need to know how to write and balance a chemical reaction, and you need to know how to identify reaction types. That last one's important because we're going to start off talking about these based on reaction type, because it's a really helpful way to figure out what may form. Okay, let's start with ta-da! Synthesis reactions. Our first synthesis reaction is this. Now, how do we know this is going to be a synthesis reaction? I mean, I suppose there are lots of possibilities, but you've got two single elements. There's no way to change dance partners here. The only thing that can really happen is that these two elements can form a compound. Well, you know it's magnesium oxide, but do you remember how to write a formula for it? Here's the thing to remember. You have now magnesium, which forms a 2+ ion, and oxygen, which forms a 2- ion. What compound are they going to form? MgO, of course. So you don't have to account for this 2. That's just there because remember, oxygen's diatomic in nature. So they're going to form MgO. The way you're going to account for the fact that you have 2 oxygen atoms starting out is when you get to balancing. Okay, well, there, it's balanced, which isn't a step you have to take, but you will eventually. All right, let's do another synthesis reaction. All right, we're given hydrogen, assumed gas, and oxygen, again, assumed gas. When we look at this, we see two single elements. So again, really the only thing that can happen is they can combine to form a compound. Well, what compound do hydrogen and oxygen commonly form? H2O. Now, we know that it's not H2O2. You are not just mashing these things together. You have to actually think about the compound they're going to form. Hydrogen and oxygen are a little harder because they are bonding covalently. It's not quite as predictable as an ionic compound, but we know that this is the synthesis of water. Now, how do you account for the numbers of atoms that you started with and the number you end with? That's your balancing step. So, 2H2O plus 1O2 yields 2 waters, 2 H2Os. And that's our final balanced chemical reaction. Let's do one more synthesis before we move on. Okay, we have iron plus sulfur, which, yes, in nature exists as S8. Weird. Well, again, we have two single elements. The only possible thing they can do is combine to make a compound. Now, this is going to be ionic. We have a metal and a non-metal, so we're just looking at what charge these things typically have. Okay, well, sulfur is easy. We know that sulfur is in the same group as oxygen, and it forms S2-, but iron's a little trickier because it can form any one of several ions. We have iron 2 and iron 3 most commonly. Here's the part you're going to like. If you are not told which iron ion is forming the compound, you're free to use whichever one you want. So I'm going to choose iron 2 because, boy, does it make the math simple. So that's going to give me FeS. In some cases you are told which ion is forming the compound, but when you're not, you can use either. So now it's down to balancing, and we show 8 Fe plus S8 yields 8 iron sulfides. Okay, let's go to our next case, which is decomposition. How do we know that this is going to be a decomposition reaction? Well, we only have one reactant, and it's a compound. There's really nothing else that can happen. And as long as this is a binary ionic compound, predicting what comes out of it is also fairly simple. Now, what can this break into? Well, mercury and oxygen. And mercury is a metal, so mercury walks alone. Remember, scary metal dude isn't holding anybody's hand. Oxygen, in nature, appears as O2, as a gas. It's diatomic in nature. We'll have to balance it, of course. Okay, what we end up with then is 2 mercury oxides yield 2 mercuries and 1 oxygen. And remember that decomposition typically happens only with an input of energy. So in this case, the mercury oxide has to be heated to get it to decompose. And we show the word heat over the arrow. Okay, again, here we have water being decomposed with electricity. How do we know it's going to be a decomposition reaction? We only have one reactant. There's nothing else that could possibly happen. What will this decompose into? Well, it's going to decompose into hydrogen and oxygen. But we have to think about what state these things occur in on their own. So, hydrogen exists as a diatomic gas, as does oxygen. We could actually put in the state information here. You cannot just rewrite those elements with their subscripts, because the subscripts in the compound tell you how the atoms are pairing up. That's not how they're going to behave once they're on their own. Okay, balanced chemical equation, 2H2O decomposed with electricity yields 2 hydrogen and 1 oxygen. Okay, so here we have a single replacement reaction. We have iron sulfide meets oxygen. How do I know it's single replacement? Because I have a compound and a single element. And that single element is going to try its darndest to get into that compound. The question that always comes up is, what replaces what? Well, the thing you have to remember is that this oxygen can only replace something that is similar to it in some way. Let's look at iron. Iron is a metal. It forms a cation. Sulfur is a nonmetal. It forms an anion. Which of these things could oxygen replace? Well, what do we know about oxygen? It's a nonmetal that forms an anion. There's no way oxygen can replace iron. Oxygen can only replace the sulfur. So what product could we possibly get? Well, we could get iron oxide and free sulfur. Remember, we have to write our formulas based on the sort of behavior we expect from those elements. And when we have an element all by itself, we have to carefully consider in what form it appears in the wild, as it were, on its own. And sulfur's that weirdo that appears as S8. Let's balance real quickly. Okay, after our replacement is finished, we have 8 iron sulfide plus 4 O2 yields 8 FeO plus an S8. Balanced, done. Note that oxygen is now occupying the spot that sulfur occupied over here. In other words, it replaced the sulfur. Okay, we now have copper 2 chloride plus aluminum. This is again a single replacement because we have a binary compound and a single element appearing here. The question is, who would aluminum try to replace? Well, let's think again in terms of what we know about these elements. Copper is a metal, and it forms a cation. What do we know about chlorine? It's a nonmetal. It forms an anion. What do we know about aluminum? Well, aluminum's a metal, and it forms a cation. So, aluminum can only replace copper. There's no way it can replace chlorine. Okay, so I've made a compound of aluminum and chlorine. I get aluminum chloride, and I've got free elemental copper. But whoa, Moser, how'd you get AlCl3? Again, you have to consider the ions that these elements form. Al forms a 3+ cation, while Cl forms a 1-. They do not carry their subscripts with them onto the product side of the reaction. Okay? Let's do one more. Oh wait, I forgot to balance that. Our final balanced form is 3 copper 2 chloride plus 2 aluminum yields 2 aluminum chloride and 3 coppers. Alright, let's move on to the last one of the single replacements. Okay, our last single replacement reaction is lithium nitrate meets sodium. Again, we want to figure out what sodium can possibly replace. What do we know about lithium? Well, it's a group 1 metal, and it forms a cation. What do we know about nitrate? Ooh, it's a polyatomic ion, but it's a polyatomic anion. What is sodium? It's a group 1 metal that forms a +1 ion. Sodium could replace lithium. Let's write the products. And in this case, boy, it's pretty easy because sodium and lithium both form a +1 cation. So we get sodium nitrate, and lithium, it's a metal, it walks all by itself. And hey, that's convenient because the charges are all the same. It's already balanced! Yay! Now let's do double replacement and then one more type. Alright, so here we're showing that we have sodium bromide and magnesium chloride. Whoops, forgot the 2. And we're going to assume, because most double replacement reactions happen in aqueous solution, we're going to assume that these two are in aqueous solution, or we've been told that. So the question is always, what goes with what? So we know how these break apart. We have a sodium ion and a bromine ion, a magnesium ion and a chloride ion. Well, what can end up replacing what? Again, the way you want to think about it is what we know about these elements. We know that sodium is group 1, forms a cation. We know bromine is group 17, forms an anion. Magnesium, group 2, forms a cation. Chlorine, group 17, forms an anion. I see a pattern emerging here. So, bromine and chlorine can swap places. What we're going to end up with is sodium chloride and magnesium bromide. Now, pay attention to the fact that this 2 is now the subscript on bromine, because bromine is partnering with magnesium, which forms a 2+ ion for bromine's 1-. Remember that those subscripts have to relate to the 2 elements that are now forming a compound. Do a quick balance. There's our finished form, 2 sodium bromide in aqueous solution plus 1 mole magnesium chloride in aqueous solution yields 2 moles of sodium chloride in aqueous solution and 1 mole of magnesium bromide also in aqueous solution. Alright, one more double replacement and then the really cool stuff. Okay, I have got silver nitrate, AgNO3, and sodium chloride. Again, we're going to say that these are all in aqueous solution because that is usually how double replacement reactions occur. What can dance with what? Well, we have silver, which is a metal and forms a positive ion, a cation. We've got sodium, which is a metal and forms a cation. We have nitrate, which is a polyatomic ion, but it's an anion, and chlorine, which is going to form an anion. Well, that tells us that chlorine could replace nitrogen, and silver could replace sodium. Let's write it up. Okay, what we get out of that is sodium nitrate and silver chloride. Again, this is one of those lovely ones where all the charges are the same. Everything forms a +1 or -1, so there's really not a whole lot of fancy footwork involved in writing those formulas. It's also based on the same thing, already balanced. Now, if you find that you're really struggling with double replacement reactions, I will tell you this. Many, many years ago, I had a student who, no matter what was done, just could not remember what could possibly dance with what. We resorted to color coding the portions of the compounds so that everything that was in the quote-unquote front, everything that was a cation, was in a red box, and everything that was an anion was in a blue circle. What this student knew in the end was that there always had to be a red circle and a blue square. If it's a trick that helps you, you're welcome to steal it. Let's talk about our last class of reaction. Combustion! Boom! Boom! Fire! Okay, never mind. Sorry, I got excited. So, we're going to talk about combustion, and specifically we're going to talk about the combustion of hydrocarbons. Okay, what do we have here? Methane, CH4, carbon tetrahydride, and it is meeting up with oxygen gas. How do we know this is a combustion reaction? Because we have a hydrocarbon and we have oxygen. There's only one thing that happens when we show a chemical reaction between a hydrocarbon and oxygen, and that is fire. Sorry. Alright, what are the products of this reaction? Oh my gosh, how do I predict that? Well, you don't really predict it so much as you memorize it. The only products of the combustion of a hydrocarbon ever are CO2 and water. Seriously, CO2 and water. Did you know that? Now, of course, these things are combusting at temperatures well above the vaporization point of water, so the water is always going to be gaseous, as is the CO2. Really, that's it. CO2 and water, no matter which hydrocarbon. So here we've got the first 4 simple hydrocarbons, simple chain hydrocarbons. We've got methane, ethane, propane, and butane. And guess what the products of this reaction are? Well, let's see. When we burn ethane, C2H6, in oxygen, oh, we get CO2 in a gas and H2O, also a gas. Huh, peculiar. Guess what we get when we burn propane, C3H8, in oxygen? Ooh, me. CO2 and H2O. Guess what we get when we burn butane in oxygen? Ooh, I know. CO2 and H2O. This H2O is the reason that you sometimes see water leaking out of a tailpipe, because guess what your car engine's doing? Combusting a hydrocarbon. So, when you see a hydrocarbon and oxygen in a chemical reaction, it is combustion of a hydrocarbon, and the only products are CO2 and H2O. We're not talking about the slightly more subtle complications of side reactions yet. We're just not there. All right, with this, you should be able to do some product prediction. Note that I did not balance any of these. We'll deal with that later. All right, take care, do your practice.